Hi guys, it's your science teacher here, back with another video. This time it's all about the first topic on physics paper 2, which is forces. The topic starts off by looking at scalar and vector quantities. Scalar quantities just have size, whereas vector quantities have size and direction. Some examples of some scalar quantities could include temperature, mass, distance, and speed. Vector quantities also have a direction, and because they often have direction, they are often forces. So some example of vectors are weight, because you have to times the mass times gravity, so it's always going down, being attracted to the centre of the earth for weight. Other vectors are displacement, which is the distance moved in a certain direction. You also have acceleration. Remember, acceleration can be positive or negative depending on which way you're going, and also velocity. Over here, to represent the difference between displacement and distance, I've drawn a house and school. Now, the distance from your house to school when you walk would be all the way that this road twists and turns, okay? So the distance will actually be a lot larger than the displacement, because the displacement is just the distance from your house to the school, whereas the distance you walk is all of this long weaving road. So the displacement is the distance moved in a certain direction, and that is why it's a vector quantity and distance is a scalar quantity. A force is a specific type of vector quantity when one object puts a push or a pull on another object. And forces can be broken down into two categories: contact, where the objects are touching, or non-contact, where the objects are not touching. Some examples of some non-contact forces when things aren't touching can be magnets. You can see attraction and repulsion when you bring magnets close together. Also, non-contact forces, gravity. You can't see gravity, but it's acting on us all the time. It's not touching us, but it's causing us pull on our bodies. Also, we have electrostatic forces as well, which happen inside atoms. The positive and negative charges in the nucleus attracting one another, keeping that atom together. That's electrostatic attraction. We also have some more common forces, which are contact forces, such as air resistance, which occurs when you are the air causes you to slow down. Air is still particles. It's not a non-contact force. Air has resistance inside it, okay? It stops you from moving so fast. You see it when you undergo terminal velocity. That's when your gravity is equal to the air resistance. Another example of a contact force is friction. You experience friction all the time. Even when you're just walking, think about it, when you rub your hands together, your hands get extremely warm. That's friction force acting just there. Any driving force, that's contact. Think about it. If you're pushing off something, or you have a car engine, the force of that engine's put in, that is going to be a contact force because it's going to be touching. Newton came up with a law about forces, showing how objects interact with each other when a force is applied, and this is called Newton's third law of motion. And Newton's third law states that when an object exerts a force on another object, it experiences an equal and opposite force. For example, if you've got a boxer and he punches a punch bag and he puts 100 newtons of force onto that punch bag is going to put 100 newtons of force back onto that boxer's glove when it touches it. Up here I've got an example of a tractor pulling a car out of the mud, And for the tractor to be able to pull the car out of the mud, the force of the tractor on the car needs to be greater than the car on the tractor for it to move. The equal and opposite force here will be the force of the tractor on the mud being equal to the force of the mud on the tractor. Free body diagrams are used to look at all the forces that act on a particular object. For example, if I was to look at a book resting on a table, it would have two forces acting on it. It will have the weight of the book that's acting on the table, and it will also have the force exerted by the table on the book, which keeps it in the same position. And this is what's known as the normal force. And the sizes of the arrows is important. They need to be exactly the same size for keeping that book at rest. And this is known as Newton's first law. And unless we apply an external force, that book will stay at rest. However, forces aren't always balanced. We know that because nothing would accelerate or decelerate if forces were completely balanced. For example, let's look at a car, for example, and we'll draw all the forces acting on the car. It has the weight of the car going down, and it has the normal force of the road acting back on it, and these are obviously the same size, okay, because of the fact if the weight force was higher it would sink down, and if the normal force was higher it would actually take off into the air, and it doesn't do that, okay. And it has other forces acting on it as well. It has the driving force of the car pushing it forward, and it also has the friction of the car acting backwards. Now, if the driving force is exactly the same as the friction, this car will be moving at a constant speed. And we can actually use numbers to represent the size of the forces, so we're going to use that as well. So let's say this driving force is 5 newtons. For it moving at a constant speed, friction must also equal 5 newtons. Now, because the weight and the normal force are going to be the same for all these diagrams, I'm not going to include them on the other two diagrams, but they do exist, obviously. So let's look at an accelerating car. Now, for a car to be accelerating, the driving force needs to be larger than the friction pulling it back. This will cause the car to accelerate. For example, if this driving force was 15 newtons, this friction was 2 newtons, that car would be accelerating. And we can actually quantify how much that car will be accelerating by a resultant force diagram. Now, this top one won't have a resultant force because it's moving at a constant speed. However, this one will, okay? And the resultant force would be 13 newtons this way, accelerating. Now, what happens if the car is not accelerating and it is decelerating? Well, it's just the opposite, okay? That's where the friction will be a lot larger than the driving force going forward. For example, if this was 15 newtons and this was 1 newtons of driving force, the resultant force would be 14 newtons going that way, and the car would be decelerating. We know that the vertical component and the horizontal component don't always add up. For example, if we look at a plane taking off, for example, that's going to have a resultant force going upwards and a resultant force going forwards. So if we were to look at the resultant forces acting on this plane, it might have a resultant force in the vertical plane of 120 newtons and a resultant force in the horizontal plane of 75 newtons. If I draw my diagrams to scale, so it's moving 120 newtons upwards and 75 newtons horizontally. So if we divide them by 10, it's easier to work with a ruler. So 7.5 centimeters in the horizontal plane, and it will be moving 12 centimeters in the vertical plane. So if I keep that as straight as possible, it will make it as easy as it can be. And then in order to calculate the resultant force, I need to measure the distance between them. So if I draw my line on for the resultant force, it is going 14.5 centimeters, which would be 145 newtons. And you can actually measure the angle and give the angle of that the resultant force is acting. When the forces don't act in the vertical plane or the horizontal plane, we need to use a different tactic in order to work out the resultant force vector. For example, this is a ship here, a big ship being pulled by two smaller ships. And both them smaller ships are at a 45-degree angle to that ship. Now that will mean that it was pulling the ship in a straight direction. That's why they are positioned there. And it will leave a resultant force acting here. Now, working out how large that force is, we need to know the values of T1 and T2, work out the tensions. Now, they're going to be the same if it's at the same angle. So if there's 2,000 newtons hanging up there, 2,000 newtons hanging up here, how can we work out how big the resultant force is pulling it forward? Well, just like in the last example where we used angles, you have to draw to scale diagrams in order to make this work. So you need to measure the length of the T1 and T2 and make sure that they're the same size. And then what you need to do is you need to use your protractor and work out where 45 degrees is, and then draw your lines going back in to turn it into a parallelogram. Then to work out the size of the resultant force, you just measure the distance here, and because it's a to scale diagram, you will get the correct answer. For this example, it should be 4,000 newtons. However, it's not always 45 degrees that you'll be working with. If it's smaller or larger, you can get smaller and larger resultant forces. You'll notice from my free body diagrams, I always draw my forces acting from the center point of the object that I'm looking at. For example, with the car, I pick the center point. Now, I shouldn't actually be doing that. I should be using something called the center of mass. And this is the point at which all the mass of an object can be measured from. Now, for symmetrical objects, it's really easy to calculate the center of mass because it's just the lines of symmetry. For example, let's look at this triangle here. It has a line of symmetry here. It has a line of symmetry here. And it has a line of symmetry here. Now you can see that the center of mass of this object will be here. The same could be said for this star, okay? If we draw the lines of symmetry on the star, you've got a line here, line here, line here, and you've got a line coming from here, and a line coming from here. And you can see they all cross in the center, which is the center of mass. However, not all objects are symmetrical. Look at this object, for example. We can't draw any lines of symmetry on it. Instead, we need a different way in order to calculate the center of mass. And the way we do that is using the setup that we've got down here. You can see that I've drawn a clamp stand. And the clamp stand is used with something called a plumb line. And the plumb line acts going completely down. Now, what you need to do with your object is you need to hang your object from your clamp stand using a boss and clamp, and pick a random point on the shape to hang it. Then you use a ruler to draw down. Then you use a ruler to show where the plumb line goes down, and you draw a line. Then what you need to do is you need to rotate your shape and do this procedure again. And where the two lines meet will be the center of mass. Now, centre of mass is extremely important for people to know, especially if you are in the transport industry, because you want to make sure your cars do not tipple over and the centre of mass needs to be quite low. For example, if I looked at some lorries, if the centre of mass is exceeded for that lorry, for example, if the centre of mass is here and it tipples out onto the sides and the centre of mass is outside the object, then that lorry will in fact tipple over. So it's really important to know the centre of mass of objects in order to make them as stable as possible. If you are doing GCSE Combined Science, well done. This is the end of the video for you. If you are doing Triple Science, just a little bit more to go. We are now going to look at moments, levers and gears, how they work and why they work. Now, what a moment is it is the turning force of around a fixed point. Some examples of moments could be a door opening or scissors acting around a fixed point, or even a spanner turning a screw. Now, the size of the moment depends on two factors. It depends on the force applied and the distance from the pivot. Now, the force for a screwdriver, for example, maybe I'm applying a force of 10 newtons and this screwdriver could be 20 centimeters long. In order to calculate the moment of that force, I would have to do 10 newtons times 0.2 meters. Remember, moments will be measured in Newton meters, and this will give me a moment of 2. Now, a spanner is an example of a lever, same with a crowbar, because they can be used in order to increase the amount of force on an object. And if I was wanted to increase the moment and increase the pressure on that screw, what I could do is lengthen my spanner or increase the force that I put on it. Here I've got another lever which could be a crowbar and my pivot would be here, and it works with exactly the same principle as a spanner does. If a seesaw is at rest, you can calculate the distance or the weight of a person by using the fact that if it's at rest, the moments will be equal for each of them. For example, if person A was sitting here and they had a weight of 60 newtons and person B was sitting here and they had a weight of 80 newtons, and I knew the length from person A to the pivot was 2 meters, I could now work out how far away person B must be for this system to be in equilibrium. So let's do that. Person A is 2 times 60 newtons will give me the moment there, which is 120 newtons per meter. And that will equal 80 newtons times the distance. So that will tell me that 120 Newton meters divided by 80 newtons will give me the distance, which is 1.5 meters. And that's how to answer these moment questions. They often like to use seesaws around this pivot, so you can calculate the moment for each of them people, and you would be able to calculate either the weight or the distance that that person is away. Gears also use the moment turning effect, and they work together to alter the speed between a driving mechanism and a driving part. If you are to look at these 3 gears working together, you'll notice that the small one looks like it's moving faster. That's because of the fact it actually is, okay? The larger wheel has more force but less speed, whereas the smaller wheel has less force but moves quicker. This is why the smaller gear is at the back of your bicycle and the larger gear will be at the front of your bicycle. If you want to change your bicycle into a higher gear and make it harder for you to cycle, you will actually be selecting a smaller gear on the back or a larger one on the front. That's because of the fact the ratio between these two sizes makes it more difficult to cycle and turn. The easiest gear to move in is when they are exactly the same size. They are in a 1-to-1 ratio, and this is what is used when you're going up steep hills. You want the cogs to be the same size, and this will mean that it's easier to cycle. Now, I hope you've enjoyed watching the video. Please remember, if you did, to like the video and also subscribe to my channel.